Hi everyone, myself Diona. Welcome to today's class. Now I know what some of you might be thinking. Algebra again? But trust me, this is a very different kind of algebra. There are no S's, no complicated fractions, just two numbers, 0 and 1. These two tiny numbers are the secret language of every computer, smartphone, and digital device on the planet. Today, you are going to understand that language. And, or, not, NAND, NOR, and certain Boolean laws. These are the 6 topics we will cover, and by the end of few minutes, each one will make perfect sense. So, what is Boolean algebra? Boolean algebra was invented by a famous mathematician, George Boole, in 1854, and his core idea was brilliantly simple. Every statement or value in the world can be reduced to just two things, true or false. We represent true as 1 and false as 0. So can you see these two circles, one red and one with green? The red 0 means false, off or low, and the green one stands for true, on or high. And these Boolean algebra can be used for designing digital circuits, logic gates, and computer chips. So, the first gate we are going to study is logical AND gate. The symbol of logical AND gate is here. If we are giving two inputs, input A and input B, we get an output of logical AND gate as A dot B. Can also be say as A and B. The key role behind this logic AND gate is both inputs must be 1 for the output to be 1. That is, look at this truth table. We can see two inputs, input A and input B. We are giving two inputs as 1, we get an output 1. If any one of the input is 0, we get an output 0. So think about a security door at a bank. It opens only if you have both a key and a correct passcode. If there is no key, it stays locked. No passcode, it is locked. Both together, it will be open. That is AND. So can you see how logical that is? AND means you need everything to be true. The next one is logical OR gate. So the symbol of logical OR gate is here. We are giving two inputs, input A and input B. It is an output A plus B. So we write this as A plus B, not addition like in max, but it is an OR operation. So we can say A plus B or A or B. So the key rule behind this logical OR gate is its output is 1 if at least one input is 1. So look at this truth table. We have given two inputs, input A and input B. If any one of the input is 1, we get an output 1. And the output will be 0 if and only if both inputs are 0. So imagine two light switches in a room, one near the door and one near your bed. If you press either switches, the light turns on. You don't need both, just one is enough. That is OR. And is straight, it needs everything. But OR is flexible, need at least one. Next one is logical NOT gate. This is the most simplest of all the gates. So this is a symbol of NOT gate, and it's also called an inverter gate because if we are giving input as 1, we get an output 0. Similarly, if we are giving an input 0, we get an output 1. So output is always the opposite of the input. So that is why it's also called the inverter. It flips the input. So look at the truth table. If we are giving an input A as 0, we get an output 1. As well as if we are giving an input 1, we get an output 0. Next one is the logical NAND gate. So it simply we can say it is a NOT plus AND. Look at the symbol of this NAND gate. If we are giving two inputs, input A and input B, we get an output Y is equal to A dot B, the old bar. Or we can say NAND of A, comma B. So the simple rule behind this NAND gate is output is 0 only when all the inputs are 1. Look at the truth table. If we are giving both inputs A and B as 1, we get an output 0. So everything else, it gives an output 1. So it's simply, well, comparing this comparison table of NAND as well as AND, we can see that for all the combinations, say 0, 0, 0, 1, 1, 0 or 1, 1, the AND gate output is 1 only if both the inputs are 1. At the same case, NAND gate output is 0. And for the AND, we know if any one of the input is 0, output will be 0. But for NAND, those cases we have output as 1. So that is the difference between AND and NAND. Simply we can say NAND is the NOT of AND. So here is something exciting. NAND is also called a universal gate. Why? Because using NAND gates, you can build any other logic gates and or not all of them. So engineers love NAND because it simplifies the chip design. Next one is the logic NOR gate. So this is a symbol of logical NOR with inputs input A and input B. Then you can get an output Q is equal to A plus B the whole bar, or we can say NOR of A comma B. So the basic rule behind logic NOR gate is NOR, that's equal to NOT plus OR. So the output is 1 only if both the inputs are 0. All the other cases, we get an output as 0. So while comparing this table between OR and NOR, you can see for all the combinations, the OR gate output becomes 0 only when both the inputs are 0. But that is become 1 for NOR when both the inputs are 0. If OR gate output is 0, NOR gate will be 1. If OR gate output is 1, NOR gate will be 0. For OR, any one of the input is 1, we get an output 1. But for NOR, if any one of the input is 1, NOR gate will be 0. So NOR gate is also called universal gate like. So that's all the logic that can be made with NOR gates alone. So this is a quick comparison table for all the gates that we have studied. Here is all the 5 gates side by side. Each column that shows what the output is for different input combinations. Say 0, 0, 0, 1, 1, 0 and 1, 1. For a quick comparison, we can focus on this column. For the input A is equal to 1 and in the input B is equal to 1. If we are giving the inputs 1, 1. For an AND gate, we get an output 1. Similarly, for an OR gate also, we get an output 1. So before we study, for AND gate, it is simply the NOT of an. So if AND gate output is 1, surely the NAND gate will be 0. For OR gate, which will be 1, then of course, an OR gate output will be 0. So NOT that only for works on a single input. Okay. So if you can read this one table, you already understand 5 of most important concepts in digital electronics. So take a moment to appreciate that. Then we are moving to the laws of Boolean algebra. So these are the certain laws of Boolean algebra, say identity law, null law, idempotent law, complement law, double negation, as well as commutative law. So these are the basic laws behind Boolean algebra. So starting from the identity law, we have A plus 0 that's equal to A as well as A dot 1 is equal to A. Similarly, we have null law, A plus 1 is equal to 1 as well as A dot 0 is equal to 0. And idempotent law, A plus A is equal to A dot A is equal to A. Here we are performing an OR operation, and similarly here we are performing an AND operation. Then we are moving to complement law. A plus A bar that's equal to 1 as well as A dot A bar that's equal to 0. If we are taking the value of A as 1, surely A complement will be 0. So 1 plus 0 almost that's equal to 1. Similarly, if A is 1, 1 dot 1 complement is 0. So 1 dot 0 that always equal to 0. Then the most important row is double negation. So A complement, the all complement, and that's equal to A. Because if we are taking the value of A as 1, 1 complement is 0, then 0 complement is 1. So that is the value of A that we taken above. Then commutative law. So that is A plus B equal to B plus A as well as A dot B is equal to B plus A. Then the most important and powerful laws of Boolean algebra is associative law, distributive law, absorption law, as well as De Morgan's theorem. So associative law, it's a grouping doesn't matter, just like in regular algebra. So a plus b plus c, we can say that is equal to a plus b plus c. Similarly, instead of or operation, here we are performing an and operation. So a, b, c, that's equal to a, b, c. Similarly, we have distributive law, absorption law, as well as De Morgan's theorem. When we are focusing on De Morgan's theorem, it is a most important theorem. It lets to convert and or in complex expressions. So a dot b, the whole conjugate, that's equal to a conjugate plus b conjugate. Similarly, a plus b, the whole conjugate, is equal to a conjugate dot b conjugate. So what we have learned today is certain gates like and, or, not, NAND, NOR, and certain Boolean laws. So have a look at this. For an AND gate, output will be 1 only. All the inputs are 1. For an OR gate, if any one of the input is 1, we get an output 1. An OR gate is simply an inverter. It flips the input. If input is 0, output will be 1. If input is 1, output will be 0. Then we have a NAND gate. It's an opposite of the AND gate. And NOR, it's an opposite of OR. Then we studied certain Boolean laws. A lot of students think electronics is difficult. But look at you. In just few minutes, you have cracked 5 logic gates and the laws of Boolean algebra. That's not a small thing. In our next class, we will build on this and solve real Boolean expressions. We will simplify circuits, draw 2 tables, and you will get to apply everything you have learned today. Thank you, dear students. See you in next class.